This is the second part of lesson 2.5, and in this section we're going to be looking at the linear factorization theorem. So this is something that should look familiar. It's just a more formal way to state something that we should already know, and that is that all polynomials can be written as the product of linear factors multiplied by a non-zero constant. So what we're looking at here is if the zeros are the C1, C2, all the way up to Cn, the way that we write our polynomial, if we know the zeros, we're going to put them into our parentheses as x minus whatever that number is. And that's why we have that sign change. We have an opposite sign in our parenthesis than when we take it out to get our zero. And so those are the zeros. And then this a in front, that is the leading coefficient. And what we'll see in these next few problems is that we must solve for this. We're going to find the leading coefficient as part of our process. So let's look at the way our directions here are stated. This is similar to what you'll see in the assignment from the textbook. It says find a third degree polynomial that has 1 in 5i as zeros and f of negative 1 is equal to negative 104. So third degree polynomial, this means that there will be 3 zeros. But only 2 zeros are given. So what we need to know is that imaginary zeros always come in pairs. And the pairs are called complex conjugates, a plus bi and a minus bi. Now in this case, the 5i that they've given us appears to be from this one. It's sort of like a is 0 in this case. We would call 5i a pure imaginary number compared to something like 2 plus 5i or 3 minus 5i, where a is something else. So we have this part. So the other 0 would have to be negative 5i. And if we think about what we just did with the quadratic formula in eventually getting our imaginary zeros, we had the plus and the minus as a result of the quadratic formula. So imaginary zeros come in pairs. If you're just given one, it's easy to get the other by changing the sign. And then we also have the real zero of positive 1. So there's our list of our 3 zeros. So now we're going to start to write this out using the format of the linear factorization theorem. Now we're not sure what that leading coefficient is yet. We are going to solve for it eventually. Right now we're just going to represent it with an a. Then we have that times the quantity x minus 1, because we have positive 1 as one of our zeros. Then we have x minus 5i for this one. And for the last one we have x minus negative 5i, but if we subtract the negative, that's really just the same thing as adding it. So that represents that last zero of negative 5i. Now the next step is to multiply this out. And my suggestion for you is to first multiply together the two factors that involve the imaginary zero. Things are going to cancel really nicely for us if we do these two versus trying to go in order from left to right. We'll still get there eventually, but it's going to be a little bit more work. So let's make a note here that we're going to FOIL these together first. All right, so when we do that, we've got x times x, which is x squared, x times 5i, just plus 5ix, x times negative 5i will be negative 5ix. Then we have negative 5i times positive 5i. So negative 5 times 5 is negative 25. I times I is I squared. All right, so let's look at simplifying this down. The 5ix and the negative 5ix, those are like terms. One's positive, one's negative, so those are going to cancel. Now for this part here, we know that I is the square root of negative 1. So I squared, if we were to square both sides, it's going to undo that square root, and we're just going to be left with negative 1. So that's an important step to know as we're multiplying this out. Anytime we see the I squared, it's really a negative 1. So this part is really negative 25 times negative 1, which is going to turn it into positive 25. So see how nice that multiplied out. That whole thing turned into x squared plus 25. Now let's go ahead and bring the pieces down in front. We still have a times x minus 1 in front of that. All right, so now we can keep going. We'll go ahead and FOIL these together next. So we've got x times x squared, which is x cubed. The inside would be negative x squared. The outside is positive 25x, and the last term is negative 25. Okay, so we are very close in having our final answer for our polynomial. The final step now is to figure out what is a. Is there a leading coefficient other than 1? And if so, we would want to distribute that through to all 4 of these terms on the inside. So we're going to use that final piece of information that they told us, that f of negative 1 is equal to negative 104. So we're going to use that to help us solve for a. That just means that when we plug in negative 1 for x, the entire value of our polynomial should be negative 104. So again, we just plugged in negative 1 for x. The function value should be negative 104. And what's nice about this statement here is now the only variable is a. So this is going to allow us to solve for a. So if we have a negative number to an odd exponent, the result is going to be negative. We'll bring down the minus sign. This part here, a negative number to an even exponent, result is going to be positive. Then we've got minus 25, minus 25. So altogether, this ends up being negative 52. That's being multiplied by a, and the result is supposed to be negative 104. So to get a by itself, we'll just divide both sides by negative 52, and we get that a is positive 2. That's our leading coefficient. So what we're going to do now is take that 2, and we're going to plug it back in for a at this step, and then we'll distribute the 2 into those 4 terms on the inside. So I'm going to rewrite this here as f of x equals 2 times the quantity x cubed minus x squared plus 25x minus 25. We'll go ahead and distribute the 2, and that will be our final answer. Okay, we've got one more example. So this one is similar to the last one, but there are a few differences in this. And so we're still finding a third degree polynomial, which means that there should be 3 zeros. They've only given us negative 5 and 4 plus 3i for zeros. And so looking at the imaginary one, we know that imaginary zeros come in pairs. So that means that 4 minus 3i is also a 0. So that's how we'll get this thing started. It's also telling us that f of 2 is equal to 91, so we can use that in the last step when we're solving for a. So we'll go ahead and get this written out. F of x equals a. Because negative 5 is a 0, x plus 5 is a factor. Now here's how we're going to do the next one. We're always thinking about doing x minus whatever the actual 0 is. We're going to put this in parentheses because that minus sign has to distribute to both parts. So we'll do x minus the quantity of our first 0, 4 plus 3i, and then we'll do x minus this quantity containing our second 0, 4 minus 3i. Now if we were to distribute the negative, this first one is going to turn into x minus 4 minus 3i. This one becomes x minus 4 plus 3i. Now, just as we did in the last problem, I'm going to encourage you to multiply together the factors involving the imaginary zeros first, because things will cancel together very nicely. Now, it's not a binomial times a binomial, so we're not actually using FOIL. It's a trinomial times a trinomial. And so I think the easiest way to think about this is we're going to do the distributive property 3 times. So we're going to start by distributing the first term, which is x. We're going to multiply that by every term in the second one. And let's start writing the results down here below. So we've got x times x, which is x squared. Then we're going to do x times negative 4, which is negative 4x. Then we've got x times 3i, so we'll write plus 3ix. So that's just the result of the first round of distributing. Now we're going to do it again with the next term here, which is the negative 4. That's going to multiply by everything. So that's going to be negative 4 times negative 4. Okay. Negative 4 times x is what I mean. That's what we're going to start with, negative 4x. Okay, now we're going to do negative 4 times negative 4 plus 16. Then we're going to do negative 4 times 3i, which is negative 12i. So that's the result of the second round of the distributive property. Now we're going to do this one more time with the negative 3i. That is going to multiply by each part. So we've got negative 3i times x, which is negative 3ix. We have negative 3i times negative 4, so we've got positive 12i. Then we have negative 3i times positive 3i, which is negative 9. And then remember that I times I makes it negative 9i squared. All right, so let's start to go through and see if there's some like terms that we could either combine or cancel. We've got a positive 3ix and a negative 3ix. We've got a positive 12i and a negative 12i. Let's see what we have left. So we're going to keep that x squared in front. We've got negative 4x, so that's going to turn into negative 8x. And then we have a positive 16 here. At the end, I squared, we know that's negative 1. So negative 9 times negative 1 is positive 9. So we're going to do that 16 plus 9, and that's equal to 25. So it was a few more steps than we did in the last problem, but it still simplifies down to be something pretty nice. Let's go ahead and bring down the front. And we're going to do our last step here of the multiplication, which again is kind of like what we just did with doing the distributive property. First, we'll distribute the x to everything on the inside of the trinomial. So we've got x times x squared. We've got x times negative 8x. And then x times 25. Then we're going to do the distributive property again. This time we're going to do it with the 5. So we've got 5 times x squared, 5 times negative 8x, and 5 times 25. All right, we'll go ahead and combine like terms now in the next step. So we've got negative 8x squared plus 5x squared. So we'll put those together. And then we've got 25x minus 40x. So those can go together. We still have that plus 125 at the end. All right, so we're very close. We've done all of the hard work of getting our polynomial multiplied out. Now we need to do that final step of solving for a. So we're going to use that fact that f of 2 is equal to 91. So that means that we're going to replace f of x with 91, and we're going to plug in 2 for x. We're going to carefully simplify this down using order of operations to help us solve for a. So looking at this inside part here, we've got 2 cubed, which is 8. Now for the next part, we need to do the exponent first before we multiply by the 3. So we're going to do 2 squared, which is 4, and then 4 times the negative 3. That's going to make that negative 12, minus 30, plus 125. That whole inside part there turns into 91. So this works out really nice. We're just going to divide both sides by 91, and we get that a is 1. And because it's 1, we actually don't need to change anything about the polynomial that we have right here in this step. We don't have to distribute the 1 in because it's not going to change it. So let's just rewrite our final answer part down here, that f of x is equal to x cubed minus 3x squared minus 15x plus 125.